I'm Jackson. I work at I work as a software engineer at StarTree. And today we're going to talk about how we integrate PromQL into Pinot. To quickly go over the agenda, we're going to cover motivation, how we put all this together as a solution. We'll do a quick demo, and we'll do a deep dive into the features implemented and our learnings. So to start the motivation, I'll talk about disaggregated observability stack. So when you think about observability vendors, they often provide a complete solution. You send them the metrics, um, they provide you with the visibility or the visualizations and storage. And this is convenient, but it does come with some trade-offs. Once you've sent your metrics over, they tend to be locked into the platform. It's not so easy to lift and shift your metrics into another service. And this is partly due to the rigid query capabilities. If you're trying to fit the query capabilities to your business purpose and it doesn't quite work, there's not many options for you. And then on top of that, you want to store a lot of data for these things, but they tend to be built on the amount of data that you're storing. And they don't have flexible storage options. So if you have a lot of historical data, you're paying the same price across it. And this leads to high vendor costs. So with the disaggregated stack, what we're trying to do is break up each individual component. So we start off with the ingestion component, data store, and then finally the visualization. When you have these individual components, it allows you to deploy this into whatever cloud stack you need. It also lets you pick the best components for each workload. This flexibility gives you more options for cost-effective storage, and it's easier to integrate into your existing business systems. I'll talk quickly about the characteristics of metrics data and some of the challenges that we face with this. So when you're collecting metrics, you tend to collect these from an entire fleet of servers, and this could be cloud servers, Kubernetes environments, and each of these are running large number of processes, and each process is probably going to have multiple threads. You want to collect metrics from all of this. So you end up with a large volume of data. And it's also important to be able to compare your metrics over time. So you might want to know, how has your reliability and performance changed over the past month, 6 months, or even a year? It's also important that we can get these metrics very quickly. Most of our reliability, the way that we respond to incidents and measure reliability, comes from these metrics. So if these metrics are slow to arrive, it impacts our ability to respond to incidents and maintain our reliability. So the common challenges that we face here is that with these metrics, they tend to have very high cardinality in our metric labels. So metric labels are going to be like the metadata attached to the metric that we measure. This could be like the name of the instance that generated the metric, the service name, and all these names tend to be unique to the individual machine or service that generated this metric. We also want to track a lot of this metadata for our metrics. And we give an example here, and you can see there's probably about like 5 keys here, 5 to 10 keys here. But these key sets grow really quickly, especially when you have very large systems. And this in turn creates very wide rows in your database. Querying can also be complex because we want to query across all the data segments at the same time, which can be physically challenging. And then indexing and ingesting this data can be tricky as well. As our labels are very dynamic. As time goes on, we're adding new labels, we're removing labels, and each of these labels individually have a higher cardinality. Pinot fits in this picture as we say, a perfect foundation for the modern observability. Pinot fits in the disaggregated stack as the query engine and data storage. Usually the Kafka is going to be involved in the ingestion piece. And once we get the data in Pinot, Pinot is designed for a high throughput ingestion and low latency queries. Its main business purpose is to compute these large aggregations across large sets of data very quickly. If the queries that we're running are too slow, we also have a lot of indexing techniques that we can apply. And Pinot also supports a tiered storage model. So if we have historical data, we can store it in more cost-effective storage solutions. Pinot is also able to scale horizontally along with your metrics infrastructure. As your metric pipeline grows and you need to have more Kafka brokers, you can scale Pinot alongside it. I want to quickly talk about why we chose to implement a time series engine and more specifically implement PromQL. So Pinot has a SQL engine, and writing time series queries in SQL can be a bit awkward. So we wanted to take advantage of existing time series query languages, such as PromQL and M3QL. To support the features of these query languages, we didn't want to try to translate these query languages into SQL. We wanted to have a native engine to support them. And the advantages we get from this is it's easier to add new functionality directly into the time series engine, as we don't have to make conversions to SQL functions. And this in turn makes it easier to support more languages. And since we're designing this engine to be solely focused on time series processing, it is generally more performant. The final piece of our observability stack is the visualizations, and we chose to go with Grafana for this piece. Grafana for StarTree is something that we've been using for a while. We're very familiar with it, and our customers do as well. So for that point, it's a very good product fit for our customers. Grafana also provides all the visualizations that we're going to need and many more, and it gives the dashboarding tools. Grafana is also open source, and it has a plugin framework, and most of the plugins are also open source, and this makes it very easy to build our plugin and connect Grafana to Pinot. Now we'll talk about the solution. So here is our metrics ingestion pipeline. The top line is before. This is what we started with. You'll see that we have a bunch of cloud environments, and within each cloud environment is an entire Pinot cluster. This is controllers, brokers, servers, and other sidecars that we use to support these Pinot clusters. They all export metrics through your typical Prometheus endpoint, and we use Vector Agent to collect these metrics. Vector Agent writes to our vector server cluster, which then would push the metrics into Pinot, and we could use Grafana to build our visualizations. Now that we've introduced Pinot into this, you can see vector server still receives all the metrics from all the environments from Vector Agent, but now it's writing it into Kafka. And from Kafka, we can ingest this into Pinot. And using the same dashboards and the same queries we were using before, we're able to now connect Grafana to Pinot. And in addition to that, because Pinot also supports SQL in these tables, we can also run SQL queries on these tables. We're able to connect Superset as well and other SQL analytics tools. So now I'll show a quick demo of the end-to-end solution here. And then after the demo, I'll hand it off to Raghav to talk us through the specific feature implementations.
Start at the Pinot console here, where you'll see I'm running this locally on my laptop and that I've got a few test tables. Let's look at the Prometheus PromQL enabled table here. You'll see the schema matches the Prometheus internal message schema. We've got the metric, which is the name of the metric. We got labels. In this table, the labels are JSON, but we can encode these in dictionary or map, as we talked about before, map giving better indexing options. The value here is the value of the metric observed at timestamp TS. Here, the timestamps are rendered as datetime strings, but Pinot internally sorts these as 64-bit integers. So now let's look at Grafana and run some queries. First thing I'm going to do is set up my Pinot data source. I've skipped ahead to the data source connection piece. You'll see my Pinot URL and broker URL here. If I had authentication tokens, I would do these here. So we'll save and test. You see that it's working. So now let's run a query. I've got my time window already preset, so we'll get some reasonable data here. And I've selected my Prometheus message table. So we saw in the table preview, we have some HTTP metrics. Let's look at request total. So we run, we get quite a lot of time series here. Let's do stacked lines. This lets us see more clearly what's going on. We've got 4 distinct time series here, and we see 4 sets of labels. Let's say I just want to look at the method, the get requests. So you'll see the autocomplete features here. This is coming from PromLens. So if you're familiar with PromLens, it's the same interface. So run the query again. And now we see 2 lines. We see our gets with a status of 500 and gets with a status of 200. Let's clean this up a little bit. These labels here are a little hard to read. So we'll say label our time series by the status. And now we have our 500 and our 200. Of course, with Prometheus, we also want to do some aggregations. So let's start off with a sum here. Here we see all of our metrics aggregated. And additionally, we can do some binary operators. We can add and subtract series, divide and multiply series. And then additionally, in the plugin, the autocomplete will only give us methods that are supported by Pinot. So when you're writing these queries, if you're looking for a function, it doesn't show up in autocomplete, probably not supported by Pinot. And at the same time, if you see a function suggested by autocomplete, you can be confident that it is in fact supported by Pinot. So we'll do one more metric here, one more time series to look at, and that's it for this demo.
Thank you, Jackson, for walking us through the demo. In the remaining slides, we'll talk about features implemented. As part of this project, we worked on building custom message decoders like Prometheus message decoder to ingest Prometheus data into Pinot tables. We worked on building map data type for cost efficiency, storage cost efficiency, and performance optimization. We worked on time series engine to enable time series data analysis, PromQL plugin to natively run PromQL into Pinot, Grafana plugin to visualize the Pinot SQL and PromQL in a unified dashboard. So as you can see in the diagram, agents collect the metrics into Kafka in Prometheus format. We use Prometheus decoder to read those messages and store in Pinot, and we use map for the labels column. And then we use time series engine and PromQL to query and then finally visualize them in Grafana Pinot plugin. So let's talk about ingestion. So for ingestion, we have a custom message decoder. Prometheus message decoder provides native support for ingesting Prometheus formatted metrics directly into Pinot table. Prometheus formats have metric names, labels, metric value, and timestamp. And the schema in Pinot is have columns like metric, labels, value, and timestamp. And this can be used to ingest any Prometheus formatted data from any source into Pinot tables. Map is a custom data type built for optimizing the storage. And map also eases the data ingestion because you don't have to worry about the flexibility of JSON in the labels. It also provides you way to separate out dense keys and sparse keys. And it also have an hybrid approach where it can automatically detect dense and sparse keys and optimize storage for you. With the help of map, the queries are much simplified now. So you can have a syntax similar to map in like Java, where you can have a labels, which is a column, and org ID, which is a key. And you can use the same syntax in other clauses like group by and filter. In the right hand side, if you see the diagram where we have the storage comparison, so the blue is basically where we store all the keys as a sparse key, which is in a EAB format. The dense where we store all the keys in a dense format and a dedicated column. Hybrid, which is a hybrid selecting some keys as a dense and some keys as a sparse, and the source data storage. And then finally, if we have to use JSON to store this data, how much space will be required? So as you see, by using the hybrid approach, gives best of both the storage as well as the performance. And we will be able to detect the dynamic dense and sparse keys dynamically and optimize both on the storage and the performance. So time series engine is a pluggable framework which allows to run time series data analysis in Pinot. We collaborated with Uber to work on this feature in open source Pinot. Time series engine is a distributed query processing, and it has two stages of execution model. The query comes into broker. Broker parses, accept the query, passes it on to the plugin. Plugin builds the logical planner and then passes it to the time series engine. And time series engine create a physical plan and then passes in the second phase is passes to the server. Server does the execution of the leaf plan and then passes the data in a series block form to non-leaf stages where plugin operators or language specific operators are executed. And this also gives you flexibility to the language developer to build language specific operators, for example, PromQL specific functions like rate and M3 QL specific operators. In the diagram, the purple blocks defines the pluggable phase where the language developer can build plugin and plug in the planner or the operators. We built PromQL as a plugin on top of this time series engine framework to natively run PromQL into StarTree Cloud. And as part of PromQL, we built our own parser, which included Java CC grammar. And then we built abstract AST tree out of it. And then from AST tree, we built a logical planner. And logical planner includes query optimization which leverages the Apache Pinot indexing mechanisms as well as doing some filter operations and build that logical planner. And out of that logical planner, it passes on to the time series engine, and time series engine execute it and return the results back. And it gives the PromQL plugin gives you the capability that without doing any SQL translation, you can run PromQL queries natively into StarTree Cloud and build a monitoring dashboard on top of Grafana. So now we build a Grafana plugin. So Grafana plugin has two pieces, Grafana frontend and Grafana backend. So Grafana backend of frontend is the visualization layer, which is built in React.js, and it fetches the data from the Grafana backend. And it has a multiple visualization type. So we have the Pinot SQL or a PromQL. It lets you edit the query. So it has a different configuration to edit the query editor, as well as providing multiple or different configuration into Pinot. Then we have Grafana backend, which is written in Golang, and it is the layer which talks to Pinot and handle all the incoming and outgoing requests. And Pinot, it also manages the Pinot resources as well as handles the query using the Pinot query adapter. So we at StarTree have internal analytics cluster where we collect metrics from all the customer environment, and we have built a central monitoring dashboard and which is used to understand the customer environments, if there are any failures, how customers are using our product, and we collect bunch of metrics, which is as of now powered by Prometheus. So the pipeline we saw in our solution deck has Prometheus. Now we replaced Prometheus with our own StarTree Cloud, and we saw a bunch of improvements, and we had a couple of learnings, and we wanted to share those learnings with the community. So in next couple of slides, we will see what those learnings were and how replacing Prometheus with StarTree Cloud helped not only in cost but in overall performance. So first win we saw was in the performance. Now we were able to ingest the real-time data at a much higher speed, and now we could horizontally scale the ingestion by adding nodes. We were also able to retain data for longer duration. We were able to retain data for more than a month, a couple of months, and running a query on 30 plus data, we saw sub-second latencies. By leveraging the new data type map, gives us 5 to 6x faster query performance. We also used some of the Pinot concepts like creating a partitioning. So we were able to create a partition on the metric name. And because most of the query in the PromQL, the queries always run on the metric as a key. So you can create a partition in a way that whenever the query is run, you can always prune certain segments, which definitely helps in data scanning and improving your query performance. We were also able to save a lot of storage we were able to get 85 to 86% compression with the map type on a low to medium cardinality matrix. By using tiered storage, by integrating tiered storage into the system, we were able to retain data for longer duration. And we were also, because of the capability of retaining the data for longer duration, and we have a better compression, we were able to define a flexible retention policies. For example, for some of the metrics, the retention was more than 30 days. For some of the metrics, it was a week or a day. We were also able to gain some operational benefits out of the system. So before this solution, we had two systems, one where we were doing the central monitoring dashboards, and then we have a product analytic dashboard, which was built on top of Pinot. Now, once we have a PromQL capability into Pinot or in our StarTree cloud, we were able to merge those two systems, and now we have a unified metrics analytics cluster, and where we have both PromQL and SQL running. By using our own StarTree Grafana plugin, we were able to build a single dashboard where we could run both SQL and PromQL queries. And we were also able to leverage Pinot's horizontal scalability capabilities to run cost-effective metrics at scale, which saves both cost as well as gives us an operational benefit. So if you want to learn more about how to build observability platform on top of StarTree Cloud, here are some of the links which you can refer. And these links also talk about how we built certain things and how Prometheus message decoder works, or what is the design for the time series engine. So, and if you have any questions, feel free to email us or ping us on Slack channel. Thank you for attending this session. And if you have any question, please do feel free to email us or talk to any StarTree representative.